So welcome to this new lecture on Static Semi 106, and today we will going to solve some more problems on friction. This is problem F 8-3 of your textbook, and it is required to find the value of this force P that can be applied without causing the two 50-kilogram crates to move, while the coefficient of static friction between each crate and the ground is 0.25. So let's first draw the free body diagram of this entire system. Okay, these two boxes are connected using this cable, and a force is being applied here. So I have shown a force here making an angle 30 degree with the horizontal, and since we have to consider the friction force because static coefficient of friction is given, and it is same between the ground and both these crates. So this force will going to cause motion of these two crates in this direction. As you can realize that this will going to cause motion in this direction. So the direction of friction force at point A and B will be in the opposite direction. So it is shown here in the opposite direction. The normal reactions NA and B are shown. The weight of box, each box is shown here on the free body diagram, and this cable will going to support a tensile force or tension in it. So I have replaced this cable with a tension force. So if you count the number of unknowns in this free body diagram, as you can notice that there are no dimensions given. So we cannot use the equation of moment, and therefore the condition of tipping cannot be checked. So these two conditions uh, goes out of consideration. We cannot use the equation of moment, and so we cannot use the condition of tipping. So therefore we are left with two equations of equilibrium now only, submission fx and submission fy, right? And so if we consider this problem as type 1 problem, so we have only two equations available, and we have how many unknowns? 1, 2, 3, 4, 5, 6 unknowns. So we have 6 unknowns and only two equations of equilibrium, right? This problem is statically indeterminate. Even if you consider uh, the free body diagram of only one block at a time, in that case you have only two equations of equilibrium. Oh, sorry, if you consider them both separately, you will have two equations of equilibrium for block A, two equations of equilibrium for block B. So that will going to make total of four equilibrium equations, but still you will see that you will have more number of unknowns, that is six number of unknowns here. So still this problem will be statically indeterminate, and so this rules out the possibility of this problem to be type 1 problem, because in type 1 problem we are not allowed to use f equals to mu n. We are only allowed to use the equations of equilibrium, and we see that if we consider this problem as type 1 problem, it is really not solvable. So this means that now we have to consider other types. So we move on to type 2 problem now, and as I mentioned, that if you consider it to be the type 1 problem, then this means that all points of contact shown in this figure will going to lie on the point of impending motion at this point, the highest peak in this figure, because at this point the force of friction is maximum, and that maximum friction force is, you all by now know that it is equal to mu times n, the maximum friction force. So if we assume, if we consider this as a type 2 problem, then the force of friction at these points can be represented by the maximum value of friction force, that is mu times n. So we have two more equations now available. Okay, so if we separately consider the free body diagram of A and B, we will have a total of four equilibrium equations, two for block A, two for block B, and we have two equations, friction equations as well. F equals to Fa equals to mu a times Na at this for this block, and Fb equals to mu b times Nb for this block. So we will going to have total of six equations, and these six equations will going to be equal to these six unknowns that are available. So this uh, you know gave us idea that this problem is a type 2 problem. And now we will going to justify this by noting down all the observations and reading this problem carefully. So they say that we have to find out the value of maximum force P that can be applied without causing the 250 kilogram crates to move. Now this is a very important statement, the first line. You have to focus that they are saying that without causing the 250 kilogram crates to move simultaneously. This means that this force P uh, will be a value that will going to initiate or is about to initiate motion of block A and block B simultaneously. And we know that in this region, below this line, in this region, there is no motion at all. Okay, there is no motion at all until and unless this value of force P increases, and arrives at this point. Right at this point, motion is just about to take place. So this value of force, at this point, the value of force P will be the maximum value of force that we can apply without causing the motion of the block. Okay, or this entire line can be rephrased, and we can say that find the minimum value of force required to cause motion. Both statements are equivalent to each other. Determine the maximum value of force P that can be applied without causing motion, or determine the minimum value of P required to cause motion. Both these statements are equivalent, and this means that this value of force P will be such that the friction force will going to reach at their maximum value at this point, because after this point these friction forces will no longer be able to maintain the equilibrium, and these two boxes will be on verge of slipping. So now let's note down the observations. So we see that by reading now the first line of this problem, we are in this position to note down the fact that in this problem indication of impending motion is actually given to us. Okay, and since no size given, so tipping and moment equations cannot be used. uh, Unknowns are six as we counted them: 1, 2, 3, 4, 5, 6. Equilibrium equations are four: 2 for this block, summation fx, summation fy; 2 for this block, summation fx, summation fy; and we have two friction equations also. So fb equals to mu b nb, and fa equals to mu a na. We can use these two equations during our solution because it's a type 2 problem. So total number of equations we have 4 plus 2 6. This is equal to the number of unknowns. So when number of unknowns are equal to the equilibrium equations plus the friction equations, it is essentially a type 2 problem, and this means that f equals to mu n can now be used during the solution. So our next step is to consider the equilibrium of crate A. Okay, consider the equilibrium of crate A, because we cannot deal this problem if we deal with this problem if we consider the entire free body diagram. In that case, we will only be having two equilibrium equations and two friction equations. That will going to make four equations and six unknowns. So the problem will be statically indeterminate. When this becomes the case, then please recall the technique that you learned in chapter number 6 while we were solving frames and machines. We have to dismantle or disconnect the objects. So we disconnected it, and we draw the free body diagram of crate A here. Okay, the weight of crate A is 50 kilogram into 9.8. Okay, this cable will going to support a tensile force, so it is tension acting away from the box A. The normal reaction will going to act upward, since the direction of impending motion is in this positive x direction, so the direction of friction force will be in the negative x direction. And now we apply submission Fy to directly get the result for Na, which is 490 newtons. and therefore since we can use fa equals to mu a and a, or mu s and a, because mu s is same for both grades, so it comes out to be 0.25 into 490, 122.5. This means that the friction force at point A is 122.5 Newton. Now we apply submission Fx on this free body diagram, and we get T minus Fa equals to 0, and therefore the tension in this cable will be 122.5 Newton, exactly when these two boxes are about to move or are at this point. So this was the things that we can retrieve from analyzing equilibrium of crate A. Now we have to analyze the equilibrium of crate B. So let's look at the equilibrium of crate B now. Draw all the free body known and unknown forces on crate B. So please note that I have shown the direction of T on block A in the positive x direction, okay, and this cable was the common connection between the box A and box B. So if I have shown it to be away from crate A, that is in the plus x direction, okay, here I have to show it in the negative x direction on crate B. But still you see that this force tension is still a tensile force because it is acting away from block B, okay. And since it was shown to be on the positive x direction on crate A, it is now being shown in the negative x direction on crate B. So this rule you also have studied in frames and machines chapter number 6. So this force P is still unknown, acting at 30 degree with the horizontal. The weight of the block B is again 50 times 9.8. NB is in upward direction, FB is in the reverse direction of motion, because this crate B is also moving or is trying to move in this direction. So applying the friction equation, the equilibrium equation, submission Fx equals to 0, you can obviously resolve this force P into its horizontal and vertical components. So this P, this is the value of the horizontal component, P cos of 30. It is in the plus x direction, so plus minus FB acting in the negative x direction, and minus T acting in the negative x direction. And in this equation, you can use FB equals to mu S and B, because this is a type 2 problem, and in type 2 problem we have a privilege to use these friction equations during our solution. So FB equals to mu S and B, and substitute this mu S and B here, and you will get this equation, and this will be your equation 1, because you cannot do anything else in this equation. So apply submission Fy equals to 0 now, and if you apply submission Fy equals to 0, you will get the vertical component of P, that is P sine 30, plus NB minus W equals to 0, and here you have equation number 2 beforehand. Okay, still P and this NB is unknown. So what you can do is that from equation number 2 you can find the value of NB from equation number 2, which is 490 minus 0.5 times P, and put this value of NB in equation 1 here. Then you will have equation 1 in terms of only one unknown, that is P. So this is what exactly I have done here. In the next step, I have substituted the value of NB in equation 1 and transformed that equation 1 in this form, and from this equation we can solve for the value of P, and the value of P comes out to be 247.2 newtons. So this will be the value of P. Okay, if we now redraw this figure, so we know that at this point This is the point of impending motion. Both our contact points were at this point because this is the value of P. This is the value of P, which is 247.2 Newton, and at this value of P, F acting at both points will be equal to its maximum value, that is mu times N. And at this point, both the crates are just about to move now. They are at point of impending motion. So this problem you uh, review again that in the beginning, it seems that maybe no indication of impending motion is given to us, and also this P is unknown to us. So it gave us a sense that maybe this problem is not a type 2 problem, but it was tricky. And once we finalized that it cannot be solved by considering only equations of equilibrium, because in type 1 problem we only have to use equations of equilibrium, we soon realized that this problem will be solved by considering it uh, some other type, and we came to know that this is basically a type 2 problem, because initially we considered that no impending motion state is defined, but afterwards we realized that actually it has been clearly defined to us, that find the value of P which can be applied to this system without causing the two blocks to move simultaneously, and that maximum value of force P can only happen at this point. And then it was decided that this point is the point of impending motion. So in other words, this was a little bit tricky question, but we revealed the fact that the impending motion state was actually defined. So friction problems can be tricky, and you have to read them very carefully, and one by one analyze your strategy, how can it be solved. Okay, then only you can reach the correct conclusion. So let's move on to another problem, and this problems is 8.47 of your textbook, RC Hibbeler 12th edition, and it says that block C, this block C has a mass of 50 kilogram and is confined between two walls by smooth rollers. So this is a wall here, and this is a wall here, and this block has been confined between these two walls through by these rollers. So you can probably imagine that if this spool is not present, if this spool would have not been present here, this block C would have slided down because of these rollers. So it is confined by between two walls by these smooth rollers. It has a mass of 50 kilogram. Okay, and if the block rests on top of the 40 kilogram spool, okay, the block is resting upon 40 kilogram of a spool, so the weight of this, sorry, the mass of this spool is 40 kilogram. We have to find the minimum cable force P needed to move the spool, the minimum cable force P needed to move the spool. We need to find this value P. The cable is wrapped around the spool's inner core, so this spool has some kind of an inner diameter attached to it, and on that diameter this rope is wrapped, and we are pulling this rope now. The coefficient of static friction at A and B are also defined, so mu A is zero point 0.3 and mu B is zero point 0.6. Now, reading this problem gives you idea that maybe this is again a type 2 problem, because they are asking about the minimum cable force. Okay, sorry, they are asking about the minimum cable force, and we know that the minimum cable force that is required to cause motion of this spool will be at the highest peak of this graph. As I mentioned for the previous problem, that it can be rephrased as minimum or maximum force. So maximum force that can be applied without causing motion, or minimum force required to cause motion, both these statements are interchangeable. So this at this point the minimum force will be required. Okay, and at this point we know that the friction force is the maximum friction force, that is F equals to mu n. So if we assume this problem to be a type 2 problem, okay, if we assume it to be a type 2 problem, then okay, we have three equations of equilibrium for this spool: submission Fx, submission Fy, and moment, because size is also defined, so we can use the equation of moment now easily. And we have two equations of friction, one at point A, one at point B. So this makes total of five equations. And how many unknowns we have? Okay, so the number of unknowns that we have is one friction force acting in this direction, which will be Fa. Okay, then one normal reaction force at this point of contact between the spool and this block C, one friction force acting in this direction at point B, and one normal contact reaction at point B here. So this is NB, and this is NA, and this is P, which is also unknown. So we have 1, 2, 3, 4, and 5 unknowns, and we have five equations: three equilibrium equations for this spool, and two friction equations in this system, one at point A, one at point B. So five equations and five unknowns, and they ask us to find the minimum cable force, and we know that the minimum cable force P will be at this point if it is to just cause motion of this spool. Now this gives us sense that it is a type 2 problem, but while we will going to solve this problem using the methodology of type 2 problem, we will be using submission Fx, submission Fy, the friction equations, and the equation of moment. Okay, so during your solution you will going to notice that you will going to have some unrealistic results. For example, if you solve this problem by using the methodology of type 2 problem, you will get Fa to be 0, and this means that Na is 0, because in type 2 problem Fa is equal to mu times Na, mu A times Na. So this gives us the result Na equals to 0, and this is physically not possible, because this contact A is not a smooth contact, so friction force should exist. It cannot be 0, and since the coefficient of friction is also given at A, this Na cannot be 0. So there is a contact, there is a clear contact between the spool and the block, so this Na cannot be 0. This is a unrealistic and not physically realistic result. Similarly, since mu A is given, Fa cannot be 0. So this will going to immediately give you idea that this problem is actually not a type 2 problem, even though it is misleading. The statement is very tricky, and it's misleading, and probably will going to guide you towards a wrong solution. But when you will going to reach this step, you will going to find out that something is wrong. So this means that it is not a type 2 problem and something is wrong. So let's look at from point of view of type 3 problem now. So in type 3 problem, we know that the total number of unknowns will always remain less than the total number of equations. So let's try to look at this problem from that perspective. So we have at least one equilibrium equation available for this block C. Okay, right? So you have one useful equilibrium equation for block C. In fact, you have two equilibrium equations: submission Fx equal to 0, submission Fy equal to 0. For uh, block C, and you have three equilibrium equations available for this spool. Okay, so this makes total of five equilibrium equations, and you have two friction equations, one for point A, one for point B. So this makes how many equations? Seven equations. We have seven equations appearing in this problem that we can utilize. And how many unknowns? One friction force here is unknown, one normal reaction here is unknown, this P is unknown. This makes three unknowns and two unknowns here. One normal reaction at A and one friction reaction. So we have five unknowns and seven equations. This means that number of unknowns appearing in this problem are less than the total number of equations. Okay, so this basically is a type 3 problem. It is not a type 2 problem, right? If you consider it as a type 1 problem, you will see that you will have five equations of how many unknowns? Five unknowns, and you have uh, three equilibrium equation for this spool. Okay, you cannot solve this problem like that as well. It will become statically indeterminate if you consider it to be a type 1 problem. So it is not a type 1 problem, and it was a little bit tricky and misleading, but we realize that it is not a type 2 problem as well. So the only possibility is that it is now a type 3 problem. And now let's list down the observations. So since size is given, equation of moment can be used. External load P is unknown. Okay, total unknowns 5. Equilibrium equations 3 plus 2 5, 3 for spool and 2 for the block C. Friction equation 2, 1 for point A and 1 for point B. So this means that unknowns are less than equilibrium equations plus friction equations, and this is a condition that is only valid for type 3 problem. So this is a type 3 problem. This means that we cannot use f equals to mu n at all points simultaneously. We cannot use f equals to mu n at all points simultaneously for type 3 problems. Please note this down. That is why I informed you that if you will going to assume this as a type 2 problem, you will going to end up with wrong results. So I did solve this problem by type 2 method, and what I get is that the friction force at point A comes out to be 0, and so the normal reaction at point A disappears, that is 0, which is not according to the condition of the problem. And this guides us that this is not a type 2 problem, and we cannot consider it as a type 2 problem. We cannot get you know casted away from the track by the wording of the problem. So you have to be very careful in reading the problem and looking at the strategies one by one. You have to apply the concept of type 1, type 2, you know, uh, type 3. And what is most important is that you have to satisfy this inequality. In each and every type, you have to satisfy this. So you see that in the previous problem, you were not able to solve the problem if you consider it to be that problem to be a type 1 problem, and then you studied the strategy of type 2 problem and you said that okay, it's a type 2 problem. In this problem, we first went through the strategies of type 2 problem, because by reading the question it was giving us idea that maybe it's a type 2 problem. But then soon we realized that it is not a type 2 problem, because it started to give us unrealistic results. It gave us the value of friction at A to be 0, normal reaction to be 0, which is not possible. So we immediately you know rule out the possibility of this problem to be a type 2 problem, and we studied the strategies of type 3 problem, which suits this problem well. So now let's you know uh, discuss this point and make this point clear, that this is a type 3 problem and we cannot use f equals to mu n at all points simultaneously. In the previous problem, we used f equals to mu n simultaneously at both the points. Okay, but here Nothing like that is mentioned. Determine the minimum cable force P needed to move the spool. And it is not clearly mentioned that from which point the spool will going to start to move, either at point A or point B. Because in the previous problem it was clearly stated that find the value of force P that moves both the crates. Here it is not mentioned, uh, because the spool is in contact at 2 points. So which point will going to move first? This is the question. So this is how you will distinguish this problem from the previous problem. And also you have listed down the observations now, and you see that if I can if I so I have only the privilege, I am privileged to use f equals to mu n at only one point, either point A or point B. So only one of the point during my solution will be at this point where f equals to mu n. The other point will still lie below this line in this region. So if I assume f b equals to mu b n b, okay, then this means that point B will going to slip first and point A will going to remain in equilibrium. And if this point remains in equilibrium, then I have to prove my assumption is correct, and I have to prove that point A remains in equilibrium. And how can I prove that point A will remain in equilibrium? I will going to calculate the value of friction force at A using my equilibrium equations, and then I will going to calculate the maximum value of friction acting at A and then compare both these values, like we did in type 1 problem, because type 1 problems are essentially equilibrium problem. Okay, so you cannot use type 1 problem here because it is clearly mentioned that something is to move, something is to move. Okay, that also, this also rules out the possibility for this problem to be type 1 problem, right? So this condition is the key. You have to satisfy this condition. If it is a type 3 problem, then this condition must be satisfied, and here this condition is clearly satisfying. So you see in this problem, in this problem this condition was not satisfying. Type 3 condition was not satisfying. Even if you split these two boxes, you are having how many unknowns? 1 2 3 4 5 6 unknowns, and you are having two equilibrium equation for this block, one friction equation 3, two equilibrium equation for this block, one friction equation 3. So the unknowns were exactly equal to the equilibrium equation plus friction equation, not less, not greater, exactly equal. So this is a type 2 problem. This condition has to be satisfied. This is the key equation that you need to satisfy for all the problems. And so now let's use the equilibrium of block C, and let's see what we can find out from this equation, from this condition, equilibrium of block C. So just redraw this block here and show all the known and unknown reactions. There is a contact reaction Na of spool acting on block, so that is why in the upward direction the weight of the block is acting downward. It is 50 kilograms, and the rollers will going to exert a normal reaction at the point of contact. So one normal reaction here, one normal reaction here, that is N1 N2. But we realize that we do not require the values of N1 and N2, so summation fx, we can skip that summation of fx equal to 0 and just apply summation of fy equals to 0, because this is what we want. And a, this value we will going to take further in the solution. So Na minus Wb equals to 0, and Na comes out to be 490 newtons. Now the next point is to consider the equilibrium of the spool. So let us redraw the spool here and show all the known and unknown forces acting on the spool, right? So this force P has a tendency of moving the spool in the this direction, in the positive direction. That is why Fa and Fb are shown in the reverse direction. So Apply summation fx equals to 0. That will give us p minus fa minus fb equals to 0. This is equation 1. Nothing more can be done from this equation. So let us apply summation fy equals to 0, which gives us nb minus na minus w, weight of the spool, equals to 0, and this gives us the value of nb, which is 882 newton. 882 newton. Okay, so we have the value of na now, we have the value of nb now. Friction coefficients are defined at both the points a and b, right? So one of the point we can consider it to be at the impending motion point, and the other one then has to remain in equilibrium, because this is the condition, strict condition for type 3 problem. You cannot use impending motion at both the points simultaneously. So if you apply moment, submission of moment about this point O, center of the spool, then this dimension, the radius of the inner diameter is 0.2, the radius of the outer diameter is 0.4, and you see that this P will going to exert anti-clockwise movement on the spool. So that is why it is negative, P multiplied by 0.6. Okay, so submission of moment. So I am applying the moment about point A, sorry. Yes, I am applying the moment about point A at this point. So at this point, from this point, the moment arm for this force point P will be uh, zero point 0.6, yes, 0.4, and so this is point, yes, this is 0.8. No. So this radius is 0.4, right? And FB has a moment arm of 0.8. That is the diameter of this outer spool, and this is clockwise. This is in the clockwise direction. So this is the moment arm for FB, and you just match the tails and draw the curl, and you get the idea that this moment is clockwise. So that is why FB equals to FB multiplied by 0.8 is the moment. And then you have to use the moment arm for P. So this P from the center, this distance is 0.4 plus 0.2 makes it 0.6, right? So the moment arm for P measured from A is 0.6 meters, right? So this is 0.4, this distance is 0.4, and the radius of the inner diameter is 0.2, so this is 0.6. So the moment arm is 0.6 for P, and it is anti-clockwise. So from this equation number 2, you get 0.6 P equals to 0.8 FB. Now you have to get the value of FB to find the value of P, because our end required result is to calculate the value of P. So let's use the first assumption. This is our first assumption A. We are assuming that point B will going to slip first and point A will going to remain stationary. So when point B will going to slip, we can use FB equals to mu B NB for point B. And since we have the value of NB with us, 882 newtons, and the friction coefficient at point B is defined to be 0.6, then this means that FB is 529.2 Newton. And if FB is 529.2 Newton, then from this equation 0.6 P equals to 0.8 FB, we can get the value of P. This comes out to be 705.6 Newton. So now you see that we have taken the first assumption. We have assumed that point B will going to slip first and point A will going to remain stationary. And this gives us the value of FB 529.2 Newton and ultimately P to be 705.6. But whether we should stop at this point and say that this P 705.6 is our result, final result, or not, because before we can claim that this is our end result, we have to verify that point A is under equilibrium. Okay, so this means that we still have to calculate Fa from our equilibrium equations, right? And if we put the value of P to be 705.6 here in equation 1 and FB to be 529.2 in equation 1, we will get the value of Fa, and that Fa comes out to be 176.4 Newton. So in order to prove that this point A will remain in equilibrium, we have to apply the check. It is a must condition. So our point B, which we assume that it is slipping, is lying at this point, the point of impending motion, and point A is lying below this point, or below this line actually, which is the line of maximum friction force. So it is lying here. If it is lying here, then this means that this is an equilibrium, and so we have to prove that this is an equilibrium. So we have calculated the value of Fa to be 176.4 from equilibrium equations. Now we have to apply the check. So for applying check, we must calculate the maximum value of friction force acting at A. That will be equal to mu A times Na. This will be the maximum value of friction force acting at A, mu A times Na, and that is equal to 0.3 times 490, because Na has been calculated previously. It was 490, and that this gives us a result of 147 Newton. And we see that the calculated value of Fa, this value, is actually coming out to be greater than the maximum value at A. So this means that point A is not lying in this region of equilibrium, but it is actually at this point. That is the point of impending motion, because the calculated value of Fa comes out to be greater than the maximum value of friction acting at point A. And we know that the maximum value of friction is given by the product mu A and A. So this means that our assumption is wrong. This assumption is not working. This assumption is wrong, and point A is actually slipping. Therefore, we need to repeat our calculations by changing our assumption now. This time we will going to assume that point B is in equilibrium while point A is slipping first, and resolve the problem. So the value that we will going to get for P will be correct. And you see that it was a really confusing, because if we go back on this slide and we see, we try to figure out our assumption that if it is a type 3 problem, once we have decided that it's a type 3 problem, then which point to take at impending point or slipping, and which point to take as an equilibrium. Okay, which point to consider in equilibrium and which point to consider an impending motion point. It was a bit uh, you know not very clearly, we cannot clearly define this, because you see that the value of Na is 490 newtons. Okay, it is 490 newtons, and the value of friction force was zero point 0.3. Sorry, friction force, the coefficient of friction was 0.3, right? So 0.3 times 490 is the friction force acting at this point. And at point B, the friction force was uh, the coefficient of static friction was zero point 0.6, which is larger than this point A. So this means that there is more roughness between this contact than there is roughness between this contact. So of course we can decide that looking at the values of static friction coefficient, okay, and the value of Na, which is 490, we can say that there is less friction force acting at point A than compared to point B. So point A will going to slip first, and point B will maybe going to remain in equilibrium. We could have done this, okay? But then again, if you look at the application point of this force P, you see it is much nearer to point B than compared to point A. So the effect of this load is more at point B than at point A, because this force is not symmetrically located relative to point A and B. So this was a little bit confusing, and I mean it's not very straightforward to assume always the right thing. So if we would have assumed that point B uh, is in equilibrium and point A is slipping, then there was no need of solving the problem again, because the assumption comes out to be correct, justified. The assumption will be justified. But if it is not justified, we have to change the assumption and repeat the problem. So in this problem, you know, uh, if we look at the application point of force P, then we say that the effect of force P is, more on point A than on point B. Okay, sorry, it is much nearer to point B compared to point A. So probably the effect of this force P is will be larger on point B and lesser on point A, and so therefore maybe this spool will slip from point B in spite of the fact that there is a larger roughness acting at point B and the friction force is large at point B. So it is not always easy to take assumption, but in some cases you can take in the first step you can take the assumption correct, and your assumption can be justified and there is no need of repeating the problem. I intentionally took this assumption because I wanted to repeat the problem and show you the complete process of type 3 problem. So that is why I assumed point B will going to slip first. Okay, but unfortunately, it comes out to be a wrong assumption, because when we applied the check for point A, it shows us that the calculated friction force of 176.4 Newton is actually greater than the maximum friction force acting at point A. So we cannot say that this force 705.6 Newton is the correct answer, and we have to repeat our calculations by changing our assumption. So this time we will going to assume that point A will going to slip first and point B will going to remain stationary. So point A will going to slip, so it will going to come here, and the force of friction at A will be maximum, that is mu A times Na, and point B now is lying in the no motion zone, equilibrium zone. So this time, since A is slipping, the force of friction is maximum at point A. It is at this point, impending motion point, which is equal to mu A times Na, gives us 147 Newton. So this is the maximum value of friction force that is acting at point A, 147 Newton. And from equation 1, we had P minus Fb equals to 147. From equation 2, we had 0.8 Fb minus 0.6 P equals to 0. So from equation number 1, we can have the value of Fb in terms of P. Fb is P minus 147, and we are using the same equations, okay? We are using these same equations 1 and 2. So this was equation 1 and this was equation 2, please remember. We are using the same equations. No need of uh, again solving this part. You only have to just reverse your assumptions and again use these same equation to solve the problem. So equation 1, we get this value P minus Fb equals to 147. From equation 2, we get Fb equals to P minus 147, and we put this value of Fb in equation 2, 0.8 Fb minus 0.6 P. So the entire equation will appear in term of P, and here from this equation you can find the value of P to be 588 Newton. So we have to prove. So as I was saying that we have now calculated the value of this load, which is 588 Newton, and by assuming that A will going to slip first, so this means that point B will going to remain in equilibrium, and therefore we have to prove now that point B is indeed in equilibrium. So let us put this value of P back in this equation and calculate FB, which is 441 Newton, and the maximum value of friction force at B will be mu B times NB, which is 529.2 Newton, and we see that the calculated value of FB comes out to be less than the maximum value of friction force acting at B. So this means that the maximum value of friction force is 429.2, which is exactly at this point, the impending motion point, while the calculated value of FB was 441 Newton, which is below this line, uh, below this red line in this region. So this means that FB is indeed in equilibrium, and therefore the calculated value of P, which is 588 Newton, is the correct answer. Previously, the value of P was incorrect because our assumption was not satisfied. So that is why we had to change our assumption and resolve the problem, get the value of P again, and then verify our assumption. And then in the end, we have concluded that this is the right value of the force that is required. And this is how we solve type 3 problem. So we have covered chapter number 8. We have solved type 1, type 2, type 3 problems. And in the next class, we're going to start chapter number 9, which is about the centroids, center of mass and center of gravity. So I would suggest you to please go through the lectures, video lectures of chapter number 8 again and again, and prepare your lecture notes and refer to the topics from your textbook. So let us meet in the next class. Thank you.